Welcome back, Physical Science 20. This is section 4.4, single displacement reactions. So in the previous video we looked at synthesis and decomposition reactions. Now look at single displacement. So many of us would not want to be without cell phones, of course. You can see this handout is a little bit dated because look at the current cell phone being used here, a flip phone. But the idea here is that the phone is made of nickel. And what happens is nickel can leave the cell phone and transfer to the skin and make this blemish that you see happening over here. So constant exposure to nickel may make skin sensitive to it. Once sensitized, the next exposure can result in an allergic reaction. Now, why does that happen? Let's take a look. All skin naturally produces secretions such as sweat, and that contains acidic compounds like lactic acids and amino acids. These compounds make sweat mildly acidic. The acidity of skin is sufficient to slowly corrode nickel from the cell phone. And if you take a look at what's happening here, nickel from the cell phone and the lactic acid on your skin, what happens here is the nickel and the hydrogen ion from the lactic acid, switch places or are displaced. And we have nickel lactate being formed and a little bit of hydrogen gas. So this occurs on your skin, and of course having that aqueous solution, that liquid solution on your skin, can damage it or cause allergic reactions. So this is referred to as a single displacement reaction. A single element displaces another one that's in a compound. So if you take a look at that's the form. So A plus BC, and we can see A and B switch places to have B by itself and AC. Or we can think of it as a puzzle piece here. A changes place with B to make this scenario. Okay, so single displacement, single element replaces another element in a compound. Single displacement reactions are useful when you need to recover dissolved metals from solution. For example, copper 2 sulfate is a common chemical used in high school labs. Each year, schools generate considerable volume of waste copper 2 sulfate. Unfortunately, dissolved copper ions are toxic and must be removed from water before we can drink it again, of course. So one thing that can be done is looking at zinc. Zinc gets rid of the copper from copper sulfate. So we have elemental copper left over and zinc sulfate solution. Zinc metal also reacts with solutions of many other compounds. In other words, zinc is a very reactive metal. It can displace or replace other elements quite easily, whereas gold doesn't. It's relatively inactive compared to most elements. So this property explains why gold is one of the few materials that is found as single elements in nature. So, and we have a little chart here which we'll look at, and it's an activity series. The more active it is, or sorry, the more reactive it is, the greater its activity is. So with this little chart, what you should likely do is just make a big circle around it. There we go, we have a funky circle there. So if we look at this list, the higher you are on this series, the greater chance you have of replacing something that's below it. So as mentioned, gold was really inactive, so it's near the bottom, whereas lithium is very active, it's at the top. So top single elements that are at the top replace elements and compounds that are below it. And of course, the further the difference is, the more quick the reaction is, as we'll see over here. So the activity series of metals, chemists have used the results of various investigations to develop this activity series. The most active metals, lithium and potassium, are at the top. The least reactive metals, such as gold and silver, are at the bottom. Hydrogen is also included in the series because it behaves like a metal. It loses an electron and becomes a hydrogen ion, the H plus ion, so it somewhat behaves like a metal. Including hydrogen also makes it easier to predict which metals react with acids. Since acids release hydrogen ions, we can figure out how something will react in an acid by looking at its effect on hydrogen. So the activity series is based on two important generalizations. The first one being one element displaces elements below it in compounds, but single elements cannot replace elements in compounds that are above it. And of course, as I mentioned, the farther apart the two elements are, the more likely it is that the displacement reaction will occur quickly. Okay, so to determine whether or not a reaction will happen between an element and a compound, you have to look at the two places on here, or their positions on here, and then from that you can figure it out. So if we look at this example here, magnesium and copper sulfate. So the question is magnesium active enough to push out copper sulfate, or to push out the copper from copper sulfate? So if we look at their placement here, copper is right here, magnesium is right here, so yes, it does. In fact, it's quite a bit higher. So magnesium is quite a bit higher than copper, so it will push copper out of the compound. So the metal element Mg is higher, therefore a displacement reaction will occur. So to figure out, so we have magnesium, copper sulfate, copper gets pushed out by itself, and to determine the new compound here, magnesium and sulfate, if we look at our periodic table, magnesium is 2+, sulfate's 2-, so they come together in a 1-to-1 ratio. Okay, so we can see single displacement. Okay, the next one, we look at lead and zinc nitrate. Lead and zinc. Will lead replace zinc? Here's lead, and zinc is above it. So lead, the individual element, will not replace zinc in the zinc nitrate solution because lead is lower than zinc on the activity series. So as you can see here, no reaction occurs because of the placement. Okay, the practice questions here. So use the activity series to write the chemical equation for the following reactions that occur. Write no reaction if you think that no reaction occurs. Otherwise, write the balanced equation, and we'll go from there. So maybe pause the video, maybe write the answers over here, and we'll see how you make out. Okay, if you had a chance to do that, magnesium and silver nitrate. So can magnesium replace silver? Magnesium is here, silver is at the bottom, so you bet it'll replace it. So magnesium will replace silver. So silver will be kicked out by itself. It's just Ag. It's not a Hofbrinkel, so it's just simply Ag. Magnesium and nitrate, though. Magnesium is 2+, as we can see here on our chart, and nitrate is 1-. So of course we need 2 nitrates for every 1 magnesium. So MgNO3, 2 is the formula for magnesium nitrate. So we have 2 nitrates. We've got to put a 2 here to get 2 nitrates. That gives us 2 silvers, so we need 2 silvers. Okay. Zinc and iron 2. Now we know this is iron 2 chloride because chloride is 1-. Since we need 2 of them to balance 1 iron, it must be iron 2. But anyway, we're just simply looking at the metals. Does zinc replace iron? So go back to here. Zinc is right here. Replace iron. Yes, there it is right there. So it should work. So iron gets kicked out by itself, and zinc has a charge of 2+, as we see here. Chloride is -1, so we need to have 2 chlorides for every zinc, and that will help us balance the equation, of course. Last one here, nickel and aluminum nitrate. So you can see we have 3 nitrates here because aluminum's charge is 3+, whereas nitrate is 1-. So we, of course, have to have 3 nitrates for every 1 aluminum. But does nickel replace aluminum? Let's check it out. Nickel is right here, and aluminum, it's above it. So nickel will not push aluminum out of the sequence there. So we can just simply say no reaction, or just NR. Okay? I think what I'll do is I'll pause the video there, or we'll stop the video. We'll go into part 2 since we almost used up 10 minutes here. So part 2 we'll look at more examples here, and there's another practice section here, part 2, and then we'll be close to getting to the assignment. Okay, we'll see you soon.